Well, welcome back. I think that some people is still at the lunch, but we are going to try to keep with the schedule. As you know, originally the next talk was going to be presented by Sanat Mostahim, that was going to come from Germany, but unfortunately she had a problem and she could not come here, and Marcelo accepted to give a fast do not require to prepare talk, so I thank him in public here because of that. His talk is going to be Graph Adjacency, Spectral Embeddings, Algorithmic Advanced and Applications. Marcelo Fiori received the bachelor degree in electrical engineer in 2008 and the master in mathematical engineer in 2011 and the PhD in electrical engineer in 2015, all from Universidad de la República Uruguay. From 2010 to 2015, he held different visiting positions at University of Minnesota and Duke University. He is currently an assistant professor with the Mathematics Department of Engineering School here at the Engineering School. His main research interests are in spectral graph theory, graph isomorphism, graph matching problem, as well as graph representation and optimization. So, Marcelo, thank you for coming.
Thank you, Martin, and for the invitation and the organizers of the event. As Martin was saying, I will talk about graph adjacency spectral embedding, some algorithm advances and applications. This will be kind of a review of a technique of embedding graphs and some recent applications and methods that we have from the last 2 years. So this is joint work with 3 colleagues here from Universidad de la República, Bernardo, Paola, and Federico, and Gonzalo from the University of Rochester. So I thank them for the work and part of the slides. So this is like inside a framework of graph representation learning. As we all know, if we have like images, sequences of images, or audio, or language and natural language processing, all these stuff that have like very very powerful structure, then we have beautiful methods that work pretty well. And when we go to the graph setting, we lose all these or part of this structure, and so part of this graph representation learning community, what they're trying to do is trying to take advantage of these methods that work very well for images or video or audio and LLP to the graph world, let's say. And we have, of course, a lot of examples from biology, social networks, gene regularity networks, chemistry, a lot of them. And the main challenges here are that it's hard to make convolutions in this, which are the key for these methods to work in image processing and audio in the graph setting. So in this talk, we're going to talk about one specific way to do graph embedding. There are other ways. This is a very nice book from Hamilton. So if you're interested in graph representation learning, this is a very nice way to introduce them. And there are kind of 2 ways to do it. One is with GNNs, with graph neural networks, and other ways are what we are doing here. So I will start with this method or this kind of model, which is the RDBGs, the random dot product graph. And I will present first the model, and then we will talk about some algorithms and then some applications. So to start, let us consider that we have a latent space, and for this time, all you need to know is that this is a subset of RD where the embeddings of the nodes we're going to live. Okay, and the generative model, the random dot product graph (RDBGs), and this is the most important part of the talk. So if anything here is not clear, please let me know. So the model is defined as this. We have a vector in RD, which is the embedding for each node in the graph. And the probability of the entry A of the metric, adjacency matrix A, IG, so if there is an edge or not between nodes I and G, is given by the following probability. It's a Bernoulli with the inner product between the embeddings of the nodes I and the nodes J. So the embedding vectors of the nodes, their inner product, codifies the probability of an existing edge between the corresponding nodes. This is the key of all the talk, basically. So and of course we have a symmetry because we are going to talk mainly for undirected graphs with no loops. So the diagonal of the adjacency matrix is 0, and so we're going to end up. So we have a graph, node structure. I'm going to end up with embeddings of each node which live in RD, and I'm going to show some examples in a few slides. And then this is the important part. We have a matrix X which consists of the embedding vectors for each node, which lives in R to the number of nodes times the dimension of embedding. You can think of D equals 2, for instance, or D equals 3. So we're going to embed each node into R2 or RD or similar. Okay? So this is a very nice model because it subsumes a very classical graph random models. For instance, the Erdős-Rényi, where each edge is independent from each other with probability P. And the more general stochastic block model, the SVM, which I'm going to explain it next because we're going to use it in an example. So the stochastic block model is defined as follows. We have like a number of communities, and we have some nodes assigned to each community, and we have probability for the nodes to be connected to nodes in the same community and to nodes to be connected to another community, which are specified by these probabilities, pi, QR. So in the first case, for instance, you have like an SVM with just one community, which is the Erdős-Rényi model. In the following, in the center, we have an RDBG, an SVM model with 3 communities. So here's a schematic of these probabilities. In these blocks, in the diagonal, we have like the very high values for probabilities, which corresponds to the probability of a node of community 1 to be connected to another node of the same community. Here, for instance, in this block, we have maybe the probability of a node from this community to be connected to a node from this community, which is very low. So we have here we capture this community structure of some graphs. And we can do like the opposite, like 2 communities, but which are like a bipartite graph, which are very connected to nodes from the other community, and this is specified with 0, for instance, in these diagonal blocks, and something different than 0 in these other blocks. So these mixtures of Erdős-Rényi graphs or models is very flexible, and this RDBG model that I presented in the previous slide is a generalization of this model. So we have a very expressive model in this sense. So this was like the generative part, but the interesting part is, well, okay, we have a graph or a sequence of graphs. How do we compute embeddings for these nodes of this given graph, for instance? So this is this part. The maximum likelihood estimator is of course we always will try to do that, but in this case is intractable for a moderately large number of nodes. So what we can do is the following. If you remember, the most important part that I said is that the entry ij of the matrix, adjacency matrix, is given, the probability of the edge is given by the inner product. So if we take this matrix X transpose, where X contains the embeddings, then the entry ij of this matrix, of this outer product, if you will, matrix, contains the inner product of the embeddings of the nodes I and j. So this is exactly the probability matrix of the model. And if we think a given graph like a noisy observation of the model, then the expectation of the adjacency matrix is exactly the probability matrix. Then what we're going to try to do is to infer or estimate matrices X such that the product, the outer product here, X transpose, is similar to the given matrix, adjacency matrix A. So we're gonna, this suggests this kind of least square regression to infer a matrix X such that X transpose is very similar to matrix A. Okay, so here we have a first optimization problem, if you want, that allows us to compute X. This is if we look at this problem, this is actually a non-convex problem in X. Sorry, this is a non-convex problem in X. But luckily, there's a closed solution to that problem that comes from taking the eigendecomposition of the matrix A. So if we take exactly A symmetric, so we can eigendecompose the matrix A as this, U, lambda, U transpose, and we take if we want to embed this graph in R, let's say 3, with D equals 3, then we take the 3 largest eigenvalues, and that we cut the eigendecomposition there, and this is exactly the solution of the problem. All right. So this is what is said here. We take the eigendecomposition, we take the D largest eigenvalues, the corresponding eigenvectors, and this is the solution of the previous problem. There is actually one comment here, that is the solution is not unique. Because of course the model is specified by means of the inner products between the embedding vectors. So if we rotate, for instance, every vector in with the same rotation, then we obtain the same probability matrix. This is of course we can reconstruct that what I just said here. If we take W, an orthogonal matrix, then the matrix X times W gives exactly the same model as the embedding X. So this is a model that it's not identifiable or is identifiable modular rotations. All right. So some examples, so you can grasp the idea of what what can we express with this model. This is exactly an SVM model with three communities, which are, these are the probabilities. This is the probability of a node from community 1 to be connected to a node from community 1, 1 to 2, and so on. And this is a sample adjacency matrix from this model. And these are the embeddings that we compute with exactly taking the eigendecomposition that I just described. So as you can see, of course, this is a synthetic example, and we have the order of the node. You can say, oh, I can see here the communities, of course, but in the graph you don't have the order of the nodes. The order of node is arbitrary, and don't be fooled by this drawing here of the adjacency matrix. I will show exactly this in a following example. But if we take then the embedding in R3, and actually the number 3 here in the dimension of the embedding is related to the number of communities. If we take the embedding, as I was saying, of this adjacency matrix, then we end up with these embedding vectors. And as you can see, we can see here that there are 3 communities. And here, so we went from a kind of a combinatorial or with no structure world of the graph to RD, where we have lots of geometrical tools we can do clustering here, for instance, which is straightforward. All right. I will show an example of exactly this in a moment. This is another classical example. This is the Sakari Karate Club. I don't know if you're familiar with this example, but it was a karate club from the 70s, and they were the graph here is like a social graph where these are members of the karate club that shared some activities outside the club, and then at some point the instructor and the administrator they had a fight, and the club split in two. And the colors here refer to the members who went with the instructor or with the administrator after the breakup, let's say. So the graph captures this the colors, and the graph captures these social interactions between the members. And if we embed this graph, you can see here that this is the embedding of the instructor, and this is the embedding of the administrator. And as you can see, sorry again. Since the inner product has two components, the modules of the vector and the angle between the vectors. Let's say if we want to consider what is the probability of the instructor here to be connected to this guy here. Okay, so maybe it's one of these. Then you have to take into account two things: the modules of both vectors and the angle between them. This is the inner product. So as you can see, all the reds and the blue embeddings of the graphs of the nodes here are in almost 90 degrees here. So this means that the inner product is very, very low. So it's very they have a very low probability of connecting one of the red guys with one of the blue guys, which again it's reasonable when we look at the picture. So I think one last example, or maybe the previous. This is the graph of collaborators with Erdos. So I don't know if you're familiar with the Erdos number, but this here in the left is the matrix of collaborators. So each node here is a mathematician, and there is a 1 there, or the number of papers that they co-author with another mathematician. Let's say the mathematician I with the mathematician J. And as you can see here, you can see no structure. That's what I was talking about like a couple of slides before. You are not able to see the structure here. But if you embed this graph and take and do like a clustering in RD, and then we permute the adjacency metrics to show that clustering, then you can see a very clear structure here. All right. And now, yes, the last example. This is a dynamic network that is the international relation between France and the UK. As you can see, from the late 19th century, it was like this is the angle, so it is 90 degrees angle. It's no relationship at all. Then with the World War II, they have like they became closer. And then this is very, 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 very aligned with angle 0 when they team up to form the European Union. This is from a paper of 2010. So I would like to see how it is now with the Brexit. So this is like what we call the vanilla model, where we have undirected and graphs with no weights. Part of what we did was to extend this to weighted graphs. And here, so we have an adjacency matrix, and we have a weight in each of the edges. And what our model specifies here is like the moment generating function. I will try to pass fast with this, but in any case, what we do here is, instead of just specifying like the expectancy of the adjacency metrics, we specify with a sequence of embeddings, not just like the first moment, but also the other moments. So like this is what is referred here. We have not just one embedding, but a sequence of embedding. The first embedding is like the vanilla that I just mentioned, and then the second and third embedding are what generates the second and third moment of the distribution function of the weights. All right, and this allows I will show, this is very easy to compute because we compute the adjacency spectral embedding, so this exact same method that I just described, but instead with matrix A, with a matrix A times A, where this time is the entry-wise product, but it's very easy to compute. And so here's an example of this. We have like two types of nodes, the red ones and the blue nodes, and the blue ones, which are kind of the different weight distribution. The first one is Gaussian, and the second one is Poisson, but with same mean. So if we compute the adjacency spectral embedding, as I was talking before, we see no difference there. But if we compute the embeddings for the A times A or A times A times A, then we can see here that they split, and we can recover that they effectively becomes from different. They become from different weight distributions. And we have consistency results for this. I know if this is maybe not important for you, but it is for if you want to use this kind of methods. You want to know if they are consistency, if the number of nodes grows to infinity, of the number of samples grows to infinity, then we have some results that proves that the consistency of these estimations. So as a summary of this first part, so because I will in the next part I will try to talk about some algorithmic advances, and then some, if we have time, with some online examples. As a summary here, we have like an RDBG model, which is very it's very expressive, and it subsumes a number of other random graph models. It's very easy to understand when you look at the embeddings of the nodes. It's very easy to interpret. And so there is a paper that is very recent here at 2022. That it says that this model, it's difficult to model sparse graphs with this model. Actually, you can do it if you let the dimension of the embedding grow to infinity. But this is like something that the community is working right now. It's a very active community. Yeah. So let me go to the algorithmic part of this. So when I said about the inference of how to compute the X, I said, oh, okay, just take the eigendecomposition of the matrix A. But maybe if the graph is large, then this is it's expensive to compute the eigendecomposition. And moreover, I also said that if you have two graphs, for instance, the embeddings are invariant to rotations. So if you compute the embedding of one graph and then the embedding of a second graph, they are independent the way you compute them, because you put the eigendecomposition in Python and it gives what it gives. So you have to do something there to align the embeddings. All right. So here our goal is to compute the embeddings in a different way that try to solve this kind of problems. So there's a very nice package in Python which is called Graphologic, which computes the RDBG embeddings, but it's based on the eigendecomposition function in SciPy. So if you take very large graphs, then it's very hard to have examples in a reasonable time. And actually, I said that what we wanted to minimize was this part here, A minus X transpose. But actually, what we want to minimize is this, because in the diagonal of A there are zeros, because we are talking about graphs with no loops, and in the diagonal of X transpose is the norm of the embeddings. So you don't want to take this into account. So we put a mask here, which the ones zeros in the diagonal and ones everywhere else, and this is the entry-wise product. So what we actually want to solve is this. So we lose the nice part that we had a closed form solution that was the eigendecomposition, but it was a closed form solution of a problem that wasn't exactly the problem that we wanted to solve. So this is exactly the problem that we want to solve. And actually, you can put in the mask matrix A, you can account for missing data if you don't have like a recommender system, for instance, that you have recommendations like users and movies, and you have a very matrix where you don't know a lot of the entries. Well, you can do that, put in the unknowns in entries here in the mask matrix M. So how do you solve this? This is like our problem now, right? This is non-convex again, and we don't have a closed form solution. So this is the goal, to give a better representation, better in the sense that this is exactly the cost function that we want to minimize at a lower computational cost, in the sense that the eigendecomposition is expensive, and in more general settings, meaning that we can allow for missing data in the setting. And the approach is very simple. It's just take gradient descent. Of course, this is a non-convex solution, a non-convex function, but it's convex with respect to x, x transpose, with respect to p. And there are some flows here that you can take. This is called factorized gradient descent, or the Procruz flow. The gradient of this function is, of course, very easy to compute, and it's this that is here. And also there is a theorem that says that this is non-convex, but if the initial point is close enough to the solution, then we have linear rate convergence to the global optimum, which is very nice. So we can do kind of cheap classical gradient descent methods to compute the embeddings. This is some numerical test. This is how the graph grows, and here in orange is the Graphologic library, the package, which is it computes the embeddings via the eigendecomposition, and this here is the gradient descent approach, which is much faster. And actually, if we can implement this using some coordinate descent methods, and it's even faster, and like 10 times faster than this. So this is very nice because we can compute embeddings from very large nodes very easily. So let me show a couple of examples. This is maybe I will skip this or go very fast through this. This is like an example where we have two parties and senators from two parties and some laws. So this is a bipartite graph. Senators from in the one part and laws from the other part, and you have an edge in between the senator and the law if that senator voted from that law for that law. And we have laws that are from this red party and laws that are from this blue party, and some laws that are kind of in the middle of the bipartisan laws. And we have some senators that were not present in the voting session, so we don't know, they're missing data there. So if you take a naive approach, like put zeros or something like that, then you don't recover the affiliation of these senators. But if you take this into account in the matrix M, in the mask matrix, then this allows us to compute exactly the embedding of these senators, and then they are exactly in the party where they belong. And I will show you a couple of more examples of this ability to compute fast embeddings. And one of these is if you have a streaming graph, so a sequence of graphs, and you want to compute the embedding of each graph and do something with that. So in this case, what we can do is compute the embedding of the first graph, and then use this embedding as a warm start for the gradient descent of the second graph. When you're going to do the gradient descent, you put that as the start, and then you do a couple of iterations of gradient descent until convergence, and the resulting embeddings are aligned because you initialize the embedding of the second graph from the solution of the first graph. I will say that again. So we have one graph. We compute the embedding of each node in this graph. Then we have a second graph, which is kind of in the time number 2 in this streaming graph. And then we initialize the gradient descent of this second graph with the solution of the first graph. then the embeddings move very very slow, and you have like this alignment between the embeddings. I will show that with this. I think this is a better example. These are I don't know if you're familiar with the Ceibal here. There are some in each institution, educational institution, there are some access points from the plan Ceibal, and we have data from here. This is a rural school. There are 6 Wi-Fi access points in the school, and we have the measuring between the power, the received power between each pair of access points. So this is our graph. This is our streaming graph. We have these measures for a number of weeks, 4 weeks in this case, and we compute the embedding of all these, all of the graphs. And what we can see here is that this node, the corresponding to access point number 4, moved from here to here in during time, or here to here. These are 2 embeddings because this is a directed graph and we have 2 embeddings, but don't worry about that. Just look at one of them. And so the access point number 4, remember that you have to take into account the angles between the embeddings, not so much the modules, but more the angles. So the angles between the access point number 4 with, for instance, this group change over time, and the access point number 4 move towards this cluster of other access points. And we went to the data, to the guy who was the administrator of the school, and effectively they moved the access point number 4 from one room to another. So we detected that in the embeddings. This is another example. This is a synthetic example. This is we have like one SBM, a stochastic block model, with 4 communities, but in the second instance, which is this, that we have 2 times here, the first time in the first row and the second time in the second row, and the communities blue and orange merge in the second time, and we want to see if each of these methods in each of these columns captures this merge of the communities, and at the same time the community red, for number 4, which is the red, maintains the probability with respect to the other communities. So we want to see exactly this behavior, like the communities orange and blue merge in the second time, and the community red stays at the same place. These other methods either fail either in one or the other of these expected behaviors. And we can also account for a varied number of nodes. There is a very naive way to do this, but it works very, very badly. This is like the error of this naive way to compute it. And with this method, we are able to capture to compute embeddings that with a bounded error over time. I know that I was not very specific through this, but I will try to cover the online part, or most of it at least. I think this is the last example of this. This is, I think, nowadays very reasonable example, which is national football teams. These are there is a data set which contains all the football matches between the national selections from, I don't know, I think 1930, maybe even before that. This in this data set is up to 2015, and we compute for each year the embedding of each national selection, right? And we fix the number of the embedding, the dimension of the embedding to d equals 7. But to show here in a plane, we project this R7 to the plane that contains most of the selections of Asia and Oceania. And this is because what we were trying to see if we capture that Australia left the Oceania Football Confederation to the Asian Confederation in 2005. And as you can see, remember that you have to look for the angle between the nodes here. Australia is here, this very aligned with the green ones here and here up to 2005, which is the Oceania teams. And then in 2015, it's more, the angle is more close to the blue teams, which are the teams from Asia. So we capture this as well in this example. So as a summary of this second part, we can compute the adjacency spectral embedding via a non-convex matrix factorization problem. The main tool here is the gradient descent, and this allows us to compute better representations that are aligned with previous graphs, and that allows us also to take into account missing data. There's code for this, that if you want to take a look at this, it is in our GitHub repository. I will show it later. But I will try to end with this other example of online point detection for streaming graphs, which is very similar to the example I just covered with the Wi-Fi access points. Actually, I'm going to use exactly the same example in a couple of slides. So we have a stream of undirected graphs like this, and we model them via random dot product graph, RDPGs, and the goal is to detect where the model changes. So we have we know or we want to detect if the model that generates the graphs changes at some point. So what we do is we compute some representation for the graphs, and we try to infer the change in the model from the embeddings or something like that. We're gonna do this or try to do this in a almost real-time fashion, so we can detect changes very quickly, and if we can, we want to have also theorems that say, okay, if there is a change here, you're going to be able to detect it. So here's the setting. We have like a training set where we know that this, for instance, in this image, these 4 graphs comes from the same model, and we compute the adjacency spectral embedding of the average of these graphs. This allows us to reduce the variance of the embeddings, and this is like the embedding, the training embedding. So this is like the model that we see at the training data. This is like two communities. You see the very high probability of this node between each other, and this is the nodes here. You can see also that they are close together and the angle between them, and so on. And what we observe is this kind of QSUM, like cumulative sum statistic, that is this X here. So X, I named this embedding X hat. So what we are measuring here is the difference between the X hat transpose, which is the probability matrix of our trained model, with the adjacency of the graph at time t, and we compute this, and we do the cumulative sum here, and the statistic here that we are using is then the norm, the Frobenius norm of this statistic. All right, and we have a first theorem here that say that this has a chi-square distribution. We are able to compute exactly the distribution here. So, and if we have the distribution, we can compute error rate bounds and thresholds for like hypothesis testing. If these statistics goes beyond this threshold, then we detect a change, and this is exactly what happens in this image. This is exactly what where the model changed, and this is the time where our algorithm detected the change. This is the statistic. The gamma here. This is in blue here. And this is the expected behavior if the model did not change. as it did change, we expected to see this variance from the expected behavior. And what this you can see here that we have some delay in detecting the. Of course, we're going to have some delay because we're doing some cumulative zoom here, but we can manage and we can specify how much delay we have there. And this is like the estimated delay we were expecting according to the model, and this is the delay what we measure. So it follows the same distribution, and we can do like instead of the cumulative zoom and here and taking like all the history of the sequence, you can do like a sliding window or something like that and forget the past and be able to detect changes fastly. And this is exactly the same example that I was showing before. These are the same rural school, and this is the same access point that move from here to here. And this is the statistic, and here's the change. So this is the expected value if the model did not change, and this is like the jump here is detected here. So we detected almost exactly at the time where they move the access points. In this case, without computing the embedding of each node, we just computed the embedding for the first training part, and then computed this cumulative sum of the difference between the x hat x transpose, which is computed just one time at the beginning with the adjacency matrix of each time. So this is very, very, very fast to compute. And so, as concluding remarks, this I just presented a family, a model which is called RDPGs with a random dot product graph, which is very expressive and allows to model a large number of graphs. If the size of the graphs is small or moderate, then you can do eigendecomposition. If you want to take a stream of graphs and do like the alignment indirectly between gradient descent, this is a very nice way to do it. And we have also like faster performance with when we do gradient descent. We can embed much larger graphs, and we can do online change detection points. And here is the GitHub if you want to try it. I will say that if you want two webs to remember from here are the first one is this where we put all our code, and all the examples here. You can reproduce the examples. The code is there. You just download the notebook or whatever, and you can reproduce all the examples. And maybe the Graphologic package, which is a very nice way to introduce yourself to the RDPG world. So thank you very much.
Is there any question? Well, first, let me congratulate you because you are letting your data sets and your code available for everyone so they can use your algorithms. And then I was wondering about the online scenarios. What size does the graph need to have so that they can be executed in a reasonable time?
Right. So, like this last part of the online detecting change and detection. So we have two parts here. First one is the training part, and as long as if the graph is small, then just a couple of graphs, you can compute a very nice embedding of the model. Of course, if you have more samples, then this is more precise. But if the graph is moderately small, then with maybe like 10 or something like that graphs, you can compute a very nice, very precise embedding. And then This is all you need for the online point detection, because then what you do is a graph comes in and you compute the difference between the adjacency of this graph with this x transpose here, and so the number of instances or samples that you need is exactly the number of training graphs here. So maybe I will say like the number of between 10 and maybe more if the model is more complex. Here, this is a very simple model with only 2 communities. If the model is more complex, then you will need more training graphs. But as I was saying, maybe in the number of tens or something like that.
And how large can those graphs be in order to make the algorithm that the computational performance is? Maybe it's kind of tricky. What is a computational performance reasonable for this? Because it depends on what you want to detect, no?
Yeah.
But if you're working with, I don't know, social network graphs, does the algorithm support it, or?
Yeah, that's a very nice question, and actually, it's very related to. So if you can compute one embedding, then the rest just follows, because it's just a memory or a repetition of. So if you can compute one embedding for the first graph, and I will move to this like dynamic graph embedding. If you can compute the embedding for the first graph, then the rest one is much more easy, because you take the first one as warm start, and then it's much faster. So maybe what I will say there is that how large can a graph be if you want to compute an embedding in this setting of RDBGs? And in this case, you can compute like for 25,000 nodes in a reasonable time. These are seconds. And as I was saying, with coordinate descent approaches, this will go very, very, very close to 0. So maybe in a couple of minutes, you can compute an embedding for a graph of this size, which is reasonable. It grows not linearly, but higher than linearly, not quadratic, so it's something in the middle. But I will say that with a graph around the thousands of nodes, you can do this with this coordinate descent approach, not with the naive eigen decomposition, because it explodes. This is almost cubic, so this is prohibitive for larger graphs. But in the thousands of nodes, I would say that this is competitive.
Fine. And the number of communities does not affect the runtime execution?
No, it affects in an indirect way, because it affects the dimension of the embedding. If you have more number of communities, so in this example that I was showing here, in this, you have 2 communities, then you can embed the nodes in R2, very, very, very nice. If you have 3 communities, like the first example that I showed, I will just quickly go there. This one. You have 3 communities, then an embedding in R3 is the way to go. If you have 10 communities, then you will need to go to R10, so the dimension of the embedding grows, and this of course affects the complexity of the algorithm. So I will say that the number of communities or the complexity of the model of the graph affects the dimension of the embedding, and this affects the complexity of the runtime of the algorithm.
Fine, thank you. Any other question? So we thank Marcelo for his talk.
Thank you very much.
Okay, I will see them.
Well, we are going to receive now Gabriela Ochoa, and she's going to present Introduction to Fitness Landscape and Local Optima Networks. Gabriela Ochoa is a professor of computing science at the University of Stirling in Scotland. Her research lies in the foundations and application of evolutionary algorithms and meta-heuristics, with emphasis on autonomous search, fitness landscape analysis, and visualization and combinatorial optimization. She holds a PhD from the University of Sussex and has held academic and research positions at University Simón Bolívar in Venezuela and the University of Nottingham in UK. Her recent work on network-based models of fitness landscape has enhanced their descriptive and visualization capabilities, producing a number of publications, including several best paper awards and nominations at leading venues. She collaborates cross disciplines in the use of evolutionary algorithms to healthcare and conservation. She has been active in organization and editorial roles within leading evolutionary computation conferences such as GECO, PPSN, and journals such as Transactions on Evolutionary Computation, and Transactions on Evolutionary Learning and Optimization. She's a member of the ACM SIG-EVO Executive Board and was recognized in 2020 in EVO Star for her outstanding contributions to the field. So let's welcome Gabriela.
Hello? It's working? Okay, gracias. Thank you, everybody. Thank you for the invitation. For me, I had to cross the Atlantic, even though I'm originally from Venezuela, but I'm living in Scotland now. So yes, the talk today is about the notion of fitness landscapes and local optima networks. So the previous talk was about graphs and networks. So this is a graph model to try to understand why some problems are harder to solve than others. A little bit about Scotland. Stirling in particular is a city who is kind of in the middle of, in between Glasgow and Edinburgh. It's a small city, about 50,000 people, and the university has 15,000 students, so much smaller than the university here. And the archetypical, Scottish castle that you can see there, and also the Wallace Monument, which is, if you remember Braveheart, this movie, it was a Scottish hero. So this is the Wallace Monument that you see. And the university has a little lake, loch, they call it there. So it's very green, very beautiful campus. Right, so many of you have heard about optimization. Optimization is an activity that can cross several industries and science as well. So this is some of the examples, those of you familiarized with operational research, so the classical problems in logistics, transportation. You can also have manufacturing, production lines. You have timetabling, scheduling. There are optimization problems also in packing, cutting and packing. Whenever you want to minimize either cost or maximize quality. So there are many, many possibilities of optimization problems. So it's a cross-cutting activity. There is an area that maybe you have heard also, search-based software engineering. You can optimize also automatically generating testing, for example. So it's an activity, optimization can be applied to many topics. As an introduction. And then the motivation of this talk is not an applied talk. It's more about using these graph, fitness landscapes and these graph models to understand. So the question is, well, sometimes some problems are harder to solve than others, and sometimes some algorithm seems to be, more suited to some problems or instances than others. And also the idea is to provide visualization tools to analyze problems and algorithms. And ideally, we want to find this more understanding of how to match algorithms or algorithm components. So it's about understanding. There is another area related to fitness landscape that, apart from understanding, the idea is also to try to apply performance prediction, so predictive models, to try to predict using features of the problem. So landscapes provide features that can be used for algorithm selection, for example. Right, so the outline of the talk, I will introduce briefly the notion of fitness landscapes, and then I will introduce these complex networks. This is a general topic that we heard the previous talk about social networks, technological networks, etc. So it's a modeling tool that can be applied to complex systems in general. And then these two models that I have been working across the years, local Optima networks were proposed in 2008, and search trajectory networks can be like an extension of local Optima networks, more related to trying to understand algorithm dynamics. And so that's the idea. So local Optima networks are more about a model of fitness landscapes, where search trajectory networks try to understand the dynamics of algorithms. So fitness landscapes is a notion that started many years ago in the 1932. So a theoretical biologist proposed this idea. And later it has been used to describe the dynamic of genetic algorithms and other search heuristics. It's both a metaphor and a mathematical object. Mathematically, it's a triplet. We have heard the notion of search space in the tutorial this morning. And we have a notion of neighborhood normally given by a search operator. It can be also a distance metric. And we have the notion of a fitness function. So the landscape, if we can use our metaphor of landscapes, is this idea of we have a search space, all the potential solutions to our problem, and then fitness is like the height, and then search is like traversing this landscape. This visualization that you see here in the bottom is actually visualizing the weight search space of a neural network. Of course, we can only visualize in 2 dimensions, so this is a crosscut of 2 weights of the neural network. So you can see that the landscape can be very complicated. You can have these plateaus, you can have ridges, you can have high peaks, etc. So it can be complex. So I mentioned that there are 3 components. You have the search space, you have the neighborhood, and this is a classical search spaces. Those of you working in genetic algorithms, the binary space, and the notion of neighborhood is you can see here like a hypercube. So there is a connection between 2 bit strings. In this case, is by size 4. If they differ in one solution, so the difference in flipping a bit or having distance 1 is what defines the neighborhood. In the case of permutation spaces, you can have swap neighborhoods, for example. And in the case of continuous spaces, normally it's defined by Euclidean distance. But, the notion of fitness landscape requires either this notion of how you say that 2 solutions are near to each other. So in the bit string space, they are near to each other if they differ in 1 bit, for example. In the permutation spaces, they differ in 1 swap. So that's the notion of neighborhoods. And the notion of fitness function is more familiar. It's the function that we want to minimize or maximize. Relevant features of landscape. So many features have been proposed to measure the characteristics of fitness landscape. I always like to use this metaphor of natural landscape. So I found this cerro in Uruguay. So it's an example of the classical example of a smooth landscape is a Mount Fuji in Japan. It's very, very smooth. So it's a notion of smooth. This cerro is also kind of smooth, even though it has a flat plateau. So yes, we can use our intuition of the features of natural landscapes to try to, characterize fitness landscapes. The notion of local optima is very important. The notion of local optima is this idea that, the point, a local optima is a solution that has better fitness than all its neighbors. And the global optimum is the solution that has the best fitness of all the search space. And there are other notions like a flat or a shoulder, etc. So the idea is that the structure of the fitness landscape is related to how hard or easy it is to solve the problem. So the smooth, it is easier to find the peak in a smooth landscape than it would be in a hard or rugged landscape. Other features of landscapes, the topology of the basins of attraction, the notion of deception, There is also, well, the notion of neutrality or presence of large plateaus that have the same fitness, and there is the idea of the global structure. So this is a tutorial, and in principle all of these metrics have a definition and a way of computing it. So I will concentrate on local optimal networks, but I wanted to give you like a general introduction. So normally, if you want to compute these metrics, you have to do what is called random walks. You have to sample the search space. And there are several metrics that you can compute, correlation for measuring ruggedness, metrics of neutrality, etc. So there are several metrics. Another characteristics of fitness landscape that I have been working on is this notion of the global structure. So the global structure of the landscape is this idea of how it is distributed. Not only, ruggedness is more like a measure that can be local, but global structure is how it is organized at a high level. Like if all good solutions are located or clustered, like in a mountain range, or they are isolated. So the fitness distance correlation is one classic fitness landscape metric, and I wanted to give you an intuition how it works. So the idea is that if you compute a set of solutions, and then you have to have the global optimum or the best found solution, and then you compute the correlation between the distance to the global optimum and the fitness. So the idea, if you have a cluster like that, is that the closer you are to the global optimum in terms of distance metric, then your fitness is better if you are minimizing. So if there is this correlation, we say that the landscape has this massive, it's called the Big Valley feature. So how does it work? Well, you can imagine it's relatively simple. So I'm here giving you a simple example on binary space. So the easiest possible function is this mean one function. So you minimize the number of ones. So this is a very smooth landscape. So what you do is you generate a set of functions, you generate either randomly, there's normally a random sample of solutions, and then you compute the fitness and the Hamming distance to the global optimum. So the fitness distance correlation plot for this mean one function will be a perfect correlation, right? And then in the other extreme, the fitness distance correlation metric will be something like that. No? So if you have a random function, then you generate a set of solutions, and then you compute the distance to the global optimum, and you will find a completely uncorrelated landscape. So this is just an illustration of how the fitness distance correlation. Of course, in the real world, we don't have these extremes. We have some correlation, but it's never like that. No? So that's the classic metric for computing the global structure. Another metric, this idea of the fitness correlation is also is related to this idea of the Big Valley structure. So basically is in many combinatorial problems, the Turing assessment problem, but also in other combinatorial, in graph partitioning, quadratic assignment problems, etc. They have been found that there is this correlation. So good solutions are not isolated. They are more like in mountain ranges, in clusters, if you like. Another feature that I have studied is the notion of funnel. A funnel is this idea, is related to this idea of the Big Valley, of having a correlation between fitness and distance. And this is a notion that started in the study of energy landscapes in theoretical physics. This is something I didn't mention, but the fitness landscape is really also a unifying metaphor, because it's used in genetic algorithms, but it's also used in the study of energy landscape of molecules. And also in machine learning, you have also heard of the loss surface. So it's this idea, you have probably heard, I got trapped in a local optima, etc. So it's an idea that can be applied to whenever there is a minimization problem. So the notion of funnel is also being studied in continuous and combinatorial optimization. So one of the contributions of, I wanted to talk about funnels is because one of the contributions of local optimal networks is to try to characterize this idea of funnels, and sometimes you can have more than one funnel. Okay, so just to illustrate again the notion of funnels, so this is the visualization of a unimodal landscape, and then a very smooth landscape. Then we have a multimodal because it has many local optima, but they are randomly distributed, and then the notion of a funnel is the idea that there are many local optima, but they are kind of organized in a coarse-grained structure, so they are not randomly distributed. So yes, and it's related to this notion of fitness distance correlation that I mentioned before, right? Okay, so introduction of complex networks. I will be quick because there was a talk before about networks, but yes, basically a network is, in my point of view, is the data-driven instantiation of a graph. A graph is a mathematical object that has been there since the 18th century, so it's a model that has a set of nodes and a set of edges. And it's been used in several disciplines. In computing, we call it nodes. In mathematics, we call it vertices. But it's a model that can be applied to to study several complex systems. And a complex network is a graph that doesn't have a trivial topology. It's not completely random. It's not regular like lattices. It's not completely random, but it has some structure, like like the internet in this example. Complex networks can evolve over time, and yes, they have been serving as a model to explain several complex systems. So the idea is that you are interested in studying the pattern of connectivity. This is an example of a social network that I found interesting, the notion of community. So this is a paper, not a very new one, but I found it interesting because the notion of community, these are each node, this is a social network, and this is in a school in the United States. So you have a division between races, so it's a friendship network, reported friendship. So it's illustrating, I think the top part is high school, and the bottom part is primary school. So you can see the groups or clusters of friendships that seems to be based by race, fortunately or unfortunately. But I like the fact that, when you are mixed race, apparently you can see the pink points tend to be, can be friends with the other groups. You can also find that there are some people that don't have friends or very few friends. So you have isolated people that don't report having any friends. And you can have, hubs in the network, people that have many friends. So this is a nice illustration of how, a visualization of a network can tell a lot about the structure, in this case, of a social network. So I got interested in network visualization. So I mentioned graphs are mathematical objects. They don't have a unique representation. So the idea of graph visualization is to find a way of representing the graph visually in a way that is not only aesthetically pleasing, but also kind of reveal the structure of the system, of the network. So this is an example of a very simple graph. And the notion of a layout, the layout of a graph is simply finding the coordinates for the nodes. At the end, we want to put this graph object into a plane, so we need to find the coordinates of each node. So this is the same graph with three different layouts, a random layout and two more structured layouts. And we can see that layout helps to see the structure of the network. You can also use, colors, you can use size to highlight features of the network. So this type of algorithms that I have been using are called force-directed graph layout algorithms. And so the idea, as I mentioned, there is not a single layout for the network. These force-directed layouts are based on a physical analogy. So each node in the network is a particle that has some electrical charge. And if there is a link between the two nodes, there is a spring. And then there is a physical simulation. Some of these algorithms actually use meta-heuristics because the idea is to minimize the energy. So, of course, I'm using a library. I'm using a library called iGraph. So the visualization, this library already implemented several of these algorithms. So this is some examples of layout algorithms. Normally they are named by the authors who proposed them. So you can see this is two types of force layout algorithms. And this is a nice animation that I found that, illustrates the same graph, but you can see how it can be visualized differently according to the layout. So you can see there the different layouts. Some of them are random, some of them are like circle, and the force-directed one. So just to illustrate that really the layout also helps to visualize the network. And as I said, sometimes it's an art more than a science to pick a good layout for what you want to choose to show. And as soon as you have a network model, you can compute many metrics. I mentioned that, in fitness landscapes, the idea is to provide metrics, and there is not a single metric that can characterize search difficulty or can characterize a metric, so there are many metrics that have been proposed. Here I categorize them into 3 categories. Distance metrics, you can compute the diameter of a network, or the average shortest path between nodes. You can compute metrics related to the topology, the connectivity pattern of the network, like the degree distribution, associativity, etc., or centrality metrics. I mentioned these hubs in the network. And there is also the metrics related to cohesion, like community structure of the network, etc. So many metrics you can compute. Yes, why do we study networks? Because the structure of the network is related to the behavior of the system. So that's the idea, that we can learn about the system by studying the structure of the network. Okay, so that brings us to local Optima networks. It's a model of fitness landscapes. And as I mentioned, it was inspired in work in energy landscape. And we proposed, more than 10 years ago, we proposed in Gecko to characterize combinatorial fitness landscape. So the idea is as follows. If we consider this our landscape, the idea is that we will have the nodes in the networks are the local optima. In this example here, we have 2 local optima, and what you see here is what we call the basin of attraction of a local optima. Is the set of points that if you run hill climbing from them, you end up in this local optima. So here we have 2 local optima. One is the global optimum. And then the notion of edges. So in order to define the local optimum network, you need a hill climbing or a local search algorithm. And the notion of edges is given by a notion of adjacency between the basins of attraction. That's the idea. If there is a node, if there is a solution in one basin of attraction that had a neighbor in the other basin of attraction, then you say that there is an edge between them. And that's the original definition of, we call it basin edges. Later we define this notion of escape edges. I think I have another slide next. That the idea is that you have a escape edge between 2 local optima. If you can perturb a solution, a local optima, you can perturb it, for example, with 2 flips, and then you run hill climbing again, and if you end in another basin, in another local optima, then you have an edge between them. But intuitively, the local optima is measuring the nodes are the peaks of this mountain range, and the edges are a notion of adjacency between them, if you like. So the whole search space is compressed in a network, which is a smaller object that we can characterize, we can visualize, and we can compute metrics. So that's the idea. This is a bit more formal slide about how to compute the escape edges. They account for the changes of escaping a local optimum after a controlled mutation. So you perturb the solution, and then you run hill climbing again. If you end up in the other local optima, then there is an edge between them. And the good thing about this definition of edges is they can be sampled. Our very early papers on local optima networks, we were fully enumerating the local optima and computing the edges, but that is costly. So to scale to larger landscapes, we were doing sampling. So I will illustrate how we do the sampling. So what I decided to do is to explain in more detail one particular example of local optima networks, which is the number partitioning problem. The number partitioning problem is a problem that is NP, so it's a hard problem, but it's not that difficult like other problems. And the nice thing about it is that it has what is called a phase transition. So let's describe the problem. You have a set of positive numbers, A, and they are taken from a random distribution from number from 1 to m. And the idea is to find a partition, a disjoint partition, such as the discrepancy between the sums is minimized. You can think that you have a pack of nodes of bills, and you want to distribute them between 2 children, let us say, and you want them to have exactly the same amount of money, if you like. It's illustrated here. So that you have a set of numbers, and the task is to divide it into 2 sets, such as the sum is minimized. So I will not explain the phase transition because it's a bit complicated. I don't understand it very well myself. But basically, there is a parameter of the problem which is measured in this way. So if this parameter is smaller than 1, then there are many perfect partitions, and the problem is easy to solve. Close to the phase transition, it becomes very difficult to solve. There are very little partitions. And then it continues to be hard. So the problems are easy, and suddenly they become very hard to solve. And that's interesting from the point of view of fitness landscape, because we want to know what is happening in the landscape, why the instances, even if the size of the search space is the same, suddenly they become more difficult. And the interesting thing is that they all have the same number of local optima, but some of, before the phase transition, they are easy to solve, and then they become hard to solve. Just a bit, just to instantiate an instance of this number partitioning problem so we have a set of numbers, and the worst solutions are those where there is a maximal difference between the two sets. So there is a 1 if belong to one set and 0 to the other. So you can see that there is some symmetry in this problem. So the solution of all zeros will have fitness 88, and the solution of all ones as well. So meaning all the numbers are in the first, so you give all the bills to one person. So there is a symmetry. So this, the worst solution, but there are also several solutions that can be optimal. So you can find several partitions that produce the same sum of the two sets, so the minimum is 0. Okay, so the idea for this problem was what makes the problem hard after the phase transition? Because they have the same number of local optima as we will see. So we decided to analyze this with local optima networks, and in this case, it's fully enumerated. So we found all the local optima and 30 instances, and we generated this model. So I want to mention again the notion of funnels, because with local optima networks, we think we bring a new way of characterizing this funnel. In this case, this is a landscape that has two funnels, a suboptimal funnel here. I think it works, yeah. Suboptimal funnels and the global optimal funnel. So what you see here is that if we characterize it with local optima networks, we will have if each node is a local optima, and the transitions are adjacent basins of attraction or escape edges. And then we can characterize, in this case, there are two funnels, by this notion of monotonic sequence. So monotonic sequence is a sequence of decreasing of local optima that are connected with decreasing fitness. So in this case, we have the two funnels, and the end of the suboptimal funnel is this blue one, and then we have the global funnel. So we extracted these fully enumerated, so each node there is a local optima, and the red is the global optima. And I am also visualizing in colors the improvements, meaning if you improve fitness or equal fitness or global. In this case, the monotonic sequence is the model that only keeps improving or equal edges. So you will see the same picture without the green. So we remove the green edges. And then the compressed monotonic model is a model that we propose to study neutral landscapes. So you will see that in the next plot there are no blue edges. What we did is to compress all the solutions that are in, if you like, in a plateau. If they have blue connections, we compress them. So basically this large landscape becomes a single funnel after compressing the connected components, the connected subgraphs that have the same fitness. And then we also added 3 dimensions. So this is a visualization of the number partitioning, all the local optima. Here we have all the edges, blue, green, and the improvement ones. And then we can see what happened as we go from an easy instance. So first let's see the two models. So this is the local optima network with all the edges. This is removing the deteriorating edges, and this is compressing the solution that have the same fitness. So you see the blue edges there are all compressed in a single node, so you can find the single funnel landscape. And this is for an easy instance. And then for the hard instance, what happened was, you can see that the number of local optima is the same. The number of local optima is 104 in all cases. There are less neutrality. You can see there are less blue edges. So this is the monotonic model, removing the green edges. But then what happened is that when we try to compress, you will see that, there is not a single funnel. It's more complicated. You can see these blue sinks, which are edges which are nodes without outgoing edges. So that is indicating that what is happening with the hard instances. So this is, again, for a larger landscape with n equal 20. So here we are traversing the difference. So this is an easy landscape. All the trajectories go into the single funnel. for a more, as you are increasing the value of k, these suboptimal sinks start to appear. So you can get trapped in this blue and not finding the global optima. So this is we found a feature of the landscape that really can help predict the search difficulty. So this is the success rate of an ILS algorithm. Let's concentrate only on the darker one, n equals 20. You can see that the success rate really decreased by with the increasing k, the complexity parameter. The number of local optima remains the same across the k parameters, so there is no change in the number of local optima for the easy and the hard instance, but there are the features related to the number of sinks and the incoming strengths of the global sink. You can see that we found a feature of the landscape that can really explain or reflect what happened, why the landscape became more difficult. So there is a very, very strong correlation between success rate and one of our network features. Okay, so in order to do sampling, and the previous work was based on fully enumerating these landscapes. In order to scale up the problem, we decided to study the traveling salesman problem, which is a very well-known problem for those of you in computing science. I don't know if in engineering, but it's the problem that there is a set of cities and there is a pairwise distance between cities. And the task is to find a tour that starts in one city, goes to all the cities and come back to the initial city, and you have to reduce the cost, right? So that's the traveling set. It's an NP-hard problem, combinatorial problem. And this is just an example that someone decided to do in the UK, the shortest possible walking tours through the pubs in the United Kingdom, just to illustrate a fun example of the TSC. So what we decided to do is to extract the local optima network for the traveling salesman problem. And in this case, we couldn't fully enumerate because we wanted to work with realistic instances. So what we did is we take an existing implementation of an iterated local search algorithm. For those of you who are not familiar with iterated local search algorithm, is a very simple but very powerful meta-heuristic. You start with an initial solution to the problem, and then you apply local search, you apply the local optima, then you apply a perturbation. Remember, a perturbation is a stronger mutation like a kick. And then you apply hill climbing again, and you continue. So if you can see, this trajectory of local optima is also generating a local optima network. The edges are, if you can perturb a solution and then apply local search, then there is a link between them, right? And in this case, you perturb the solution, you apply local search, and you get to the local optima, to the global optima, so it's generating a local optima network. So basically what we did is to take the iterated local search, and we instrumented it, adding every time you find a new local optima, you add it to the AL set there, and every time you find a new edge, you put it in the edges set. So this process is generating a local optima network, and you can see it in this animation here. So this is running iterated local search on an instance. So at the beginning, it's very easy to find, you apply perturbation local search, and the beginning is very easy to find an improving solution. As you are traversing the search process, it's become harder and harder to find. So this is an ILS that only accepts improving. No? So when you see this flower, and I put this because this is an example of running an algorithm, and it really looks like a virus or something. But the explanation is that's what is happening. As you progress in the search process, it becomes harder to find an improving solution. So the incumbent solution there is in green, in blue, and then the improving path is painted in green. So the process of running the algorithm is generating this network. So this is what we did. We extracted the local optima networks of instances. This is a randomly generated instance from two distributions. So the random instances the cities are placed random, and the clusters instances are placed in clusters. So even though these two instances have the same number of cities, their global structure is different. The clustered instance has a single funnel, and the success rate of iterated local search is 100%, whether the uniform instances are harder to solve, and the explanation is that there are several suboptimal funnels. So the search, this is based on sampling, so with I think it was 1,000 runs, And we run this ILS, we record the local optima, and we constructed the local optima network. So if we visualize it in 3D, when I see 3D is that I put the fitness as the third coordinate. So this is a single funnel explaining why the traveling salesman is easier to solve for cluster cities, and for uniform cities you have these suboptimal funnels. We also apply to city instances for the TSP, so this particular instance seems to have two funnels. So what is interesting here is that, that's why we have to run meta-heuristics many times, because if you are lucky and you start in the global basin of attraction of the optimal funnel, you will end up finding the global optimum. But if your initial solution happens to be in the basins of attraction of the suboptimal funnel, with this algorithm, you will get trapped there. Regardless of, you can run the algorithm 1,000 generations more and you will not escape there. So that explains why, sometimes we need to run, and the starting condition of meta-heuristics are important. Okay, so just when I was exploring visualization, this is different cities, just to cities around the world. These have several funnels, and some of the instances that have neutrality were producing this type of plots. So these are not difficult instances. They have here almost every round finds the global optimum, but there seems to be a lot of neutrality and a big plateau at the bottom. But just for fun, I was visualizing different types of instances. Okay, so we also applied, and most of the work has been in combinatorial optimization, but recently we decided to apply these local optima networks to continuous fitness function. Those of you working in optimization probably have heard of these these are very artificial functions that have many, many peaks. So the Ackley function, Rastegian, and de-Rastegian. And so of course we can only visualize them in this way if we have two dimensions, X and Y. So what we did is to extract the local optima networks using something called basin hopping, which is similar to iterated local search, and there is an implementation of basin hopping inside Pi. And so it's basically perturbation and local search. So we extracted it for 5 dimensions, and we extracted the local optima networks. And what was interesting is that we observed a very similar structure than what you can only see for 2 dimensions, but here for a 5 dimension using network visualization, it's interesting that you can see a similar global structure. So in a way, the networks allow us to visualize larger dimensional landscapes. Okay, so we have also used this model to study, algorithms that have crossovers. So instead of having only perturbation edges, we have crossover edges between the offspring between the parents and the offspring. So there is some of our work that has explored these hybrid models for local optima networks. Okay, so the next part of the talk, I will present these search trajectory networks, which are more recent. And the idea of search trajectory networks is that there are not too many visualization tools to understand the dynamic of algorithms. So those of you working on evolutionary algorithms probably have seen this type of curve. No? So we visualize only the objective space or the fitness space. So we have 2 variants or 3 variants of the algorithm, and we want to see the convergence. So we have time, and we have fitness, and we can see how the dynamic of the algorithm works. But the idea was to explore also what happened at the level of the search space, not only on the objective of fitness space. And also to be able to apply local optima networks, or a model, a graph-based model, to algorithms that may not have a local search algorithm in there. So that's the main motivation. So search trajectory networks are a tool for analyze the behavior of a meta-heuristic. So the nodes are not anymore restricted to a local optima. They represent a state of the search process. For example, if a population-based algorithm, it can be the best in the population. And the edges represent time, basically, just 2 consecutive solutions, because normally meta-heuristics are iterated processes. So if they are consecutive, there is an edge between them. So we apply this model to, and this is a case study on using search trajectory networks for analyzing population-based algorithms in continuous function. And the other innovation here, well, we applied to 5 functions, I think, but I'm showing here only 3. quadratic function, which is easier to solve, and the Michalewicz function is more complex because you have this plateau, and this is a very rugged function. So another innovation that we did here is to combine in the same trajectory, in the same network model, the trajectories of two algorithms. So we are comparing differential evolution, which is a very competent algorithm for continuous optimization. I will not go too much into the details of the algorithms. And the other algorithm that we compare was particle swarm optimization, right? So they are different in the way they traverse the search space. The differential evolution uses as mutations the difference between other individuals, while the PSO is a swarm-based algorithm. The entire population guides the process. But what I wanted to talk about is this idea of using search trajectory network to compare the dynamics of two algorithms. So a little bit of definition. So I mentioned that the nodes are not anymore a local optima. And also we needed to do this mapping between solutions and locations because there are too many, I mean, especially in continuous space because you have precision. So what we decided to do is to kind of box the search space into locations in order to be able to visualize it. And basically build a network where the nodes are locations corresponding to representative solutions and the edges connect consecutive locations in the search process. So this is how we conducted this experiment, 10 runs per algorithm, a number of function evaluations, and this is what I must mention in the mapping. So if we have a solution in 5 dimensions, we were not using all the the decimal digits, we were rounding it to only 1 decimal digit, and then we were using that to be able to kind of box the search space. So this is the visualization. As I mentioned, we are combining the trajectories of 2 algorithms, 10 trajectories. Each solution is the representative solution with this, boxing of the solution. So we can see here that we can compare the trajectories of differential evolution and PSO. So they start in the same, in this particular example, they were starting in the same initial solution. For a very easy problem, all of the trajectories were converging into the global optimum, which is represented here. So we have 2 colors, one color for PSO and the other color for differential evolution. So that's the easy function, but then with the most complicated functions, we start to see difference between the performance of the algorithms. So PSO, some of the trajectories of PSO were not able to locate the global optimum. I forgot to mention that the size of the nodes here is indicative of the incoming strength. So the larger the node, the more it acts as a hub or an attraction to the search process. So you can see here this dark point, which is not the global optimum, but is attracting many trajectories. So many of the PSO trajectories in pink get there and they are not able to escape. The thickness of the edges represent as well in the sampling process how many times there was a transition between, you can see a thick blue edge arrow there indicating that it was possible for differential evolution to escape. I think, of course, this is we cannot visualize in 5 dimensions, but we speculate that this represents the plateau, right? It represents some sort of plateau. So only one of the algorithms is able to escape. So this model allows you to see which areas of the search space are attracting the process and give you a bit more information than only the performance curve. For the very multimodal function, you also see that PSO gets completely lost. Each trajectory of PSO ends up in a different part of the search space. And in this particular case, differential evolution was more successful. Okay, so to conclude, in this particular example of search trajectory network, it seems that this variant of PSO, this particular variant, was not very good for multi-funnel rugged landscapes and landscapes with neutrality. And more generally, we argue that STNs offer insight into the convergent behavior of algorithms of any meta-heuristic, and it allows you to observe which areas of the search space are attracting the process. Right, this concludes my talk. A little bit about, as a summary, well, the idea of these tools is to offer some visualization tools to observe both the problems, why some problems are harder than others, or why some algorithms are better than others, and hopefully this can help into illuminating and improving the search network. There are a few resources as well. I should have an R package like Leslie. I don't have an R package yet, but there are some code that we have published there. There is very recently a web-based application for STN, so I invite you to explore it. Thank you very much. So I'm happy to take questions. Thank you.
Well, I will begin with local optimal networks. I was wondering what happens like in genetic programming when you're working with symbolic regression, that you don't have nothing. You have explored that kind of problem?
It's very difficult to use local optimal networks for genetic programming because you need to have a notion of local optima, no? So you have to be the best in the neighborhood. So the neighborhoods for genetic programming are so large. But we have applied search trajectory networks. We submitted something to Evolstar with Wolfgang Banzaf, and we are applying search trajectory network to a very simple linear program, linear programming, and allows this. It has a lot of neutrality, but it's not local optimized networks. It's more search trajectory networks. Yeah, and we have applied also to. Sometimes in my keynote I will talk about applying local optimal networks to neural architecture search. And there, of course, is a restricted search space. It's not the whole. So in this neural architecture search, sometimes you evolve only one part of it, and that you can find local optima there. But yeah, local optima are really restricted to, you have to have a local optima or a hill climbing, and you have to be able to find, or at least approximate the local optima. Yeah.
Wow. And I was also wondering about, you mentioned to use the information from local optimal networks to develop new operators or that try to exploit some properties of the fitness landscape. Can you make a brief comment on which is the current state of that line of search?
They have been, of course, these features are not easy to compute, no? But because they require a sampling process, but there have been some work in which we have used predictive models of, it's a predictive model where you have two algorithms and you want to predict the hitting time, the best. So you want to separate you have two algorithms and you have a set of features and you want to predict which algorithm is going to be better for a particular instance. So we have used long features and they have been very good at predicting. Another thing that can be done is, for example, perturbation strength in iterated local search. So we have studied the perturbation strength. Remember, so you perturb a solution and then apply local search. So the stronger the perturbation, in principle, you can jump further away. But there is a sweet spot of the perturbation strength. So too large a perturbation, it degenerates into random search. Too small perturbation, then you cannot escape. So it allows you to explain, why the number of funnels reduces, for example, so the instance becomes smoother in the global structure sense. But to be fair, it has been more like an understanding visualization tool. And when I have worked with co-authors, sometimes the visualization seems to inspire them. Okay, so this is what is happening, so maybe we can do this. So it's less systematic, let us say, but apparently the visualization can bring sometimes insights. So, yeah. Basically, what you want, if you, a metaphor between search and a structure of a network, of course, you want a network that is well connected, no? It's well connected, meaning wherever you start the search process, you will end up finding the global optima. So a solution that, is either a local optima that have many disconnected components is hindering that, it will be difficult to search, or the notion of funnels. We also study a little bit the acceptance criteria, the acceptance, so the funnel structure. This is a paper last year in Gecko. The depth, we try to study the depth of the funnels. So if the funnels are very deep, it is better to be greedy and accept only improvements. But if you have many shallow funnels, maybe we prove empirically that it's better to have something like simulated annealing acceptance, no? So sometimes you accept deterioration and that can help you go to a different funnel. But if you have a very deep funnel, it's better to be greedy, because there is a path. So there is a correlation between the global structure and the acceptance criteria, for example.
Well, thank you. Is there any other question? No? Well, so thank you, Gabriela, and we'll see now at the coffee break.
Thank you very much.
We have now Well, welcome back. Our last talk in the school. It will be a tutorial on graph neural networks with application by Federico Larroca. Federico Larroca received the degree in telecommunications engineering from Universidad de la República here in 2006, and the PhD degree in computer science and networking from Telecom Paris Tech at Paris, France, in December 2009, under the advisory of Professor Jean-Louis Rougier. He's currently an assistant professor with the Engineering School of the Universidad de la República. He was a researcher engineering postdoc with Telecom Paris Tech from January to March 2010, and also from 2004 to 2011, he held a teaching assistant position with the Universidad de la República. His research interests include the analysis and modeling of communication systems and development on software-defined radio. So, Federico.
Thank you for the introduction, and welcome to my talk. So this is a tutorial, and the idea is that if you have any doubts or question or whatever, you may interrupt me, and I'm more than grateful if you do so. So let's start. So you probably assisted to Marcelo's talk today, and I'm sure you know that graphs are a good model for several problems. Just to mention a few examples we'll use during the talk. Here I'm showing a graph that includes words and the number of times they appear in the same sentence. So this is a text by a certain author, and that's the same graph for another author. And the idea there is to identify who's the author of these two books or whatever. Another example, here we have molecules, and what we would like to do in the bottom. This is the molecules, and we would like to do is to predict a certain property of the molecule. In this case, it's to predict its odor. It may be, for instance, toxicity or side effects or things like that. Well, the other typical example, and the one that motivated me first for my background is on electrical engineering, telecommunication, is wireless networks, but you may think about most telecommunication networks as a graph. Another example is you have the number of drones that you would like them to perform a certain task, for instance, to move so that they don't collide between each other. And there's a communication network that's going on there, communication between the drones. So there you have another graph. And the example we'll use at the last part of the talk is we have a certain set of measurements from a set of APs, and we would like to know at which position we are in. So for instance, right now I'm in this room. I would like to know if I'm in this room, if I am in the hallway, or if I'm outside, by measuring the power from I don't know how many APs there are in this building, but there are 20 APs. I measure the power. I would like to know at what room I am. So those are examples that with the tools I will discuss now, they may be addressed with the tools I will discuss today. And the idea behind these techniques is to try to emulate, in a way, convolutional neural networks. So, how many in the room know what a convolutional neural network is? Many. Okay. So, the idea in convolutional neural networks, for those that don't know what it is to simply take a local operator in a given region of that may be thought of as an image. An image is basically a matrix, and we take a local operator. For instance, you may think about it as an average, but we may weight different parts of that patch with different weights, and by doing that, we obtain another matrix, and that's repeated, stacking several layers one over the other. That's the very short introduction to convolutional neural networks, but the idea here is that we would like to do something similar to convolutional neural networks where the context is a very structured data. It may be thought of as a matrix. But now we have a situation like the one in the right, where we have a very irregular structure. We don't have now that each pixel has 4 neighbors. We have that the neighborhood of each node maybe the neighborhood of each node may have different number of neighbors. It's very irregular. So that's the challenge that we would like to address with graph neural networks. So this is the outline of the talk that I will give today. First of all, we're going to define what graph neural networks are, and we will do it by emulating convolutions, but translating them into graphs. Then we will talk about one property in particular, this permutation equivariance. There are two, stability to changes and transferability. I will only give the references to these two properties, but they are important. So if you would like to go deeper into this subject, you may check them out. And finally, I'm going to explain an example that will try to illustrate what we've learned in the talk. So let's start by talking about convolutions. We're going to try to extend convolutions to graphs. So for those that come from an electrical engineering background, or for those who have a time of signal processing background, I'm sure this will help you in understanding what's going on. So imagine we have a discrete time signal as the one that's shown here, and the most important concept of one of the most important concepts for signal processing is that there's an importance, or there's information in the neighborhood of this signal. So it's not the same that x1, which is somewhat large, is close to x2, which is not so large. That gives you some information. In this case, if there is much difference between contiguous values, that means that you will have a signal that has large bandwidth, for instance. So let's try to do this more explicitly, and we will, for instance, try to draw a graph that gives you that structural information by simply joining with an edge two nodes that are consecutive in time. So now we have the two important characteristics, or as it says there, constitutive elements of signal processing. The signal itself, the values of x1, x2, x3, and the structure that's underlying this signal. So we now may talk about a graph where we have edges and we have nodes, we have edges. So this is another example. We will have this other more general graph than the one that's on the above. And what we do is we include signals. So we now put for each of the nodes, we include a certain value that is going to be the graph signal on this particular graph. And what we're going to do is study it as a matrix. And that carries an aspect of graph signal processing that's going to be important down or later on the talk, that we're going to order these nodes, and that order is completely arbitrary. So here is somewhat natural, the ordering, 1, 2, 3, 4, because there's first node 1, then node 2, node 3. Here I'm using 1, 2, 3, 4, but actually that's a decision I took. I could have taken any other one, but by indexing the nodes, I may study this graph as a matrix. So we may use the adjacency matrix. The adjacency matrix puts a 1 in the position where position ij has a 1 where nodes I and j are neighbors. We may also use, well, this is the adjacency matrix for the more general graph, the lower graph. We may also include or use the Laplacian, I don't know how to pronounce it in English, Laplacian. But in any case, we have a matrix that represents our graph. So, as I mentioned before, that gives you a certain order that's completely arbitrary, and we're going to discuss that later in the talk. And instead of considering a given matrix representation of the graph, we're going to simply talk about matrix S, and it will be called graph shift operator, and that I want to make it clearer now. So, convolutions. We have, if you remember your discrete time signal processing course, what we do is we take our discrete signal, so this is our original signal, if you remember from before, and what we do is we simply delay it one sample, or we first multiply it by a certain coefficient h0, we delay it a single time step, and then we multiply the signal by h1, we delay it again, this z a la minus z to the minus 1, it's a one time delay. We multiply it by h1, and then we do the same, we multiply it by h2, and then we do again, and multiply that for h3, and that defines as this discrete time convolution that I rated here. It's simply the signal delayed by a certain number of steps, multiplied by the corresponding coefficient. So that's discrete time convolution. If we think about it as a graph, so the only thing I've done here is we have our signal, and now I'm substituting it by the graph. And what we do now is, it's the same, the convolution is exactly the same operation, but what we will do now is to use our matrix representation of the graph to perform this delay operation here. So instead of using z power of minus 1, we'll try to do that by multiplying it by a certain matrix. And that is performed simply by multiplying, in this case, by multiplying the column vector by the adjacency matrix. So that simply switches the entries of the vector, and what we obtain is what's drawn here. We have the original signal, x1 in position 0, x2 in position 1. We multiply it by z, and we have x1 in position 1, x2 in position 2. We multiply it again by s, by the adjacency matrix in this case, and we obtain that. That's for the adjacency matrix. That's very, very easy to see it, but we may use any other matrix representation of our graph. But in this way, it's very clear the analogy between discrete time and graph shift operator. So imagine we have this case now, the general graph I've shown before. So in this point here, so now let's move a little bit backwards in time. See here the formula here we had before the classical convolution. I simply substituted by multiplying by the powers of the graph shift operator. So now we have the addition of the original signal times the number of delays I had before of the graph signal, graph shift operator. Of course, multiplied by the coefficient, the corresponding coefficient. So again, if we take a look at the graph I've shown before, we have that at the first, and simply seeing or taking into account the signal at node 1, we have that at the first, in this position, at node 1, we will have only the signal of node 1. When we multiply by s, we will see the signal of node 2 and 6, because they are neighbors. So there we take that signal from the neighbors. We multiply again, and we will get the information of 2 hops away. We get the information from nodes 3, 5, and 1. And we may do that again, and we get from almost all of the graph, and we may do this again and again and again. So this defines graph convolutions. And the idea is, again, I repeat it, is that for each of these multiplications, I take information for each of these powers shown here, I take information from neighbors more and more apart in the graph. Again, another example, but now I want want you to remark that, or to notice that we may use the same graph for different, the same filter for different graphs with naturally different results. So, for instance, in the case on the left and the right, we start by node 4, for instance, in this case, he will get the information x4. In the second step, he will get from the 4 connected neighbors. But now, the graph on the left will get information from the whole graph, whereas the one in the right will only get information from that sort of community there, the left community. And in the next step, he only gets from up to node 10. So, what I would like to highlight here is that once we've defined the filter, we may use it on different graphs without problem, but we have to be very careful on what happens when we change from one graph to the other. So that's convolutional graphs. Now we're going to define GNNs based on this. So empirical risk minimization is simply, or at least for this talk, learning is equivalent to empirical risk minimization, and that's simply we have a training set where we have a certain set of values that I'm including here only x, but it typically includes x and y if they're labeled. If it's unsupervised learning, it's only the x. We have a certain loss function, and what we do is we define a certain family of functions where we would like to learn, and we simply search for the function between or in my family that minimizes the average loss. So the idea now is, and I'm going to discuss that when I compare this to a fully connected neural network, is that the idea is that the system should work for values that it did not observe. And that's something I want you to keep in mind. We're interested in graphs, so why not use graph convolutions to solve one of our problems here, for instance, the one of finding where in what room we are. So assume we have a certain signal, and what we would like is to choose a filter that predicts another signal on the nodes, in this case, by simply filtering my graph signal. So that's my entry X, my graph filter, and that's the output. So learning is simply choosing the minimum, and that's something that's important. We are always looking for the coefficients of the filter that minimizes our cost. The graph is given, and I'm highlighting this in blue, because the graph is given. Someone has chosen it, or someone has estimated it. We are only focusing on choosing the filters or designing the filter. So, what's the problem? The problem is that filters can only, say, express or we can only obtain linear functions between x and y in this case. So why not equip it with non-linearity, and that gives us a perceptron. So this is a graph perceptron. We take the output of our filter and put it through a pointwise non-linear operator, for instance, the classical ReLU or sigmoid or whatever you like. But the important thing here to note is that it's a pointwise operator. So we have, if we have a single number per node, we will take the ReLU of each of those entries separate. And that gives us a perceptron, a graph perceptron in this case. And what we're looking for is exactly the same as before. The function, the nonlinear function is given, and we're still looking for the filter that provide us with the best estimate. And finally, a GNN is simply stacking several of these graph perceptrons. So here I'm stacking 3. So we have these 3 perceptrons stacked one after the other. And we take our input X, we pass it through our first layer, we connect the output of the first layer and connect it to the second, and again the output of the second to the input of the third layer. And that's all. So that's a GNN, and I don't know if there's any question this far. No question at all. Very good. So again, the idea is always, in this case, what we want to learn is the filter for each of these layers. They may be, for instance, here I use big K for the 3 layers, but they may be different. We may use different orders of filters for the different layers. Again, the graph is given, and it is important to highlight here that the S, for instance, if we think of S as the adjacency matrix, it's the importance of the signal of my neighbors for my own prediction. So the larger the weights on the graph, the more it will be taken into account when computing the output. So there's like a, when designing the graph, that's what should be kept in mind. The only difference between a graph and a GNN is simply at the point-wise nonlinearity. That a GNN works much better than a filter. It's something that may be surprising. The first thing is that it's more expressive. That's true, but there's something more going on there. We may, and there are several works, I'm going to cite them later on, that try to more fundamentally analyze what's going on there and see what's the real difference between a filter and a GNN. Again, our graph is a parameter that is given to us, but we may change it. No, we may, for instance, typical example is we've trained our system. We are Netflix, and we are training our recommender system to recommend new movies to our users. And we probably won't train our GNN with the full database of, I don't know how many millions of users Netflix has and how many thousands of films it has, but we may train our system on a smaller subset of users and movies, and then apply our filter, the filter that we've learned, to the larger dataset. And the hope there is that it should work. Again, there are other works that, analyze when that's the case or why that should work, or in which case that should work. And I'm going to, I don't know if I have them here, but the same authors I cite later on have done some works on that direction. So that's what I'm saying here. We may transfer our GNN to different graphs, and in certain situations it should work. So I've talked this far about numbers, so each of the nodes may have a single number so far, but we may have, for instance, I don't know, their users, we may have several features per user, I know, geographical information, gender, I know, how much information per user Netflix has about us, but it obviously has a lot of information. So we would like to have a signal that has several dimensions. That's no complication at all. We may think of our graph signal as a vector now. So for instance, we have, this is our original signal with a number per entry. This is our original graph of 11 nodes. So we have 11 numbers, but we may stack several dimensions, and we may end up with several features per node. And what we've discussed so far works almost equally. We now have, instead of I'm going to go a little faster here, but instead of having a single coefficient here, before it was small h, now it's a matrix. Since we may also have different dimensions per layer, so that to think it more easily here, this matrix adapts the dimension between layers so that we may start with, I don't know, 10 features and with only one. So this part, I think that it's relatively simple. So maybe you've come to this talk and you maybe installed or tested Python Geometric or any other libraries of learning over graphs, and no one has talked about graph convolutions. This is the web page of Python Geometric, or PyG as it's called now, and it talks about message passing, not convolutions. There are several papers on learning on graphs, and they don't talk about convolutions. They mostly talk about these functions aggregate, or these functions combine, things like that. You may even have taken a look at the course of Shurer Escovech, which is nice enough to leave all its resources available online. And again, these are some slides, and it talks about this again, message passing and aggregating. But if you take a closer look, what these works present are to simply take the signal on those neighbors that are only one hop away. So it's basically what I've just presented for filters of only one tap. Or two taps, it's my own signal and the ones from the neighbors. So what I've talked before is the same as the things you've maybe seen if you've read about graph neural networks, but for single taps filter. Here there's a small list of some famous papers on the area, where I try to make like a matching between what I presented so far and this paper. And this is the list of that they are called convolutional layers in Python Geometric. There's like a very large list, but believe me that what we've talked so far is exactly the same or very similar with small changes to what's more mainstream in graph neural networks. So let's talk about how can we use what we've seen so far in some canonical, I put there, but typical problems in graph learning. Again, learning on graphs, it's simply minimizing a certain cost. For instance, if you're going to make regression, the cost is typically an L2 loss, the square normed. If you're going to do classification, for instance, we would like to know if a certain the area of a certain paper in a citation network, if that's a classification problem, and the loss there it's typically cross entropy loss. That's the one even here, where we have, in this case, 5 categories. And I'm not going to talk that about, but the techniques that are used for this optimization are the same as when in any deep learning problem, and we may use Adam, Adagrad, or whatever you like the most. But let's talk about problems in graphs specifically. So they typically fall in 3 categories. The first one is node level prediction. Again, for instance, we would like to decide whether a node or user in a social network was actually a bot, or we would like to, again, that's the example I talked before, we would like to classify the discipline of a certain document on a citation network, if it's mathematics or it's biology or whatever. Or the other, very typical, is we would like to interpolate the signal. For instance, we have nodes that are users, and the edges are if they have similar tastes. So we have ratings for a certain movie, and we would like to predict if that user would like this given movie. So how do we do this node level prediction? Well, we simply take the output of our GNN, the last layer, and we pass it through a fully connected, for instance, linear layer. Or we may, for instance, concatenate several other fully connected deep neural networks. So the objective here is to use a GNN to take into account that structure, that's our a priori, and apply a vector learning method to that output. There may be something you are thinking here. It's a problem. There are certain nodes that we have to take out to train our system because we have the taste or the rate. For instance, we have the ratings for several users, and we would like to train our system, so we have to take one of these nodes out of our training part. So what do? We take like the whole node, or we leave that node with an entry of 0, and we leave our GNN to operate on the whole graph. So the two possibilities exist. The first one is called transductive, typically known as transductive, where we leave the node in the GNN and we train with the whole graph. And the other possibility is in the inductive context, where we take out the training nodes, we train our GNN, and then we execute it to perform the output. We incorporate these nodes that we left. The other example, or the other typical problem in GNNs is to try to predict or estimate something about the edges. For instance, again, if our graph is users are nodes and content are other nodes, we would like to know if this user will like that content. That's a edge prediction problem. We may, for instance, we have measurements of attenuation between points, and there's some that we don't know. We may estimate it through a graph. There are several examples here, but you get the idea. And what we do in this case is we take the output of our GNN and pass it through a function that takes as an input both of the output of the GNN of both nodes. So we would like to predict what would be the weight between node I and node J. So we take the output of our GNN and pass it through a function that will also be trained during our the training phase. Now this is maybe, for instance, a fully connected network or whatever trainable function we want to use. For instance, here I'm using an inner product. It should be differentiable to perform a gradient descent, or we may, for instance, multiply by a certain matrix in the middle, or we may use whatever we want, but we take the output of our GNN of one node, of the other node, and we use a function that takes these two inputs to predict if this edge exists or what's the weight between these two nodes. So again, you may think, well, what do we do about training? We may use like a single graph and take out edges for training, or we may be lucky enough to have several graphs and perform training on these different graphs by taking out some of the edges and trying to predict on other graphs. The final type of example is predicting a certain property of the whole graph. So that's more similar to supervised learning. For instance, we want to determine who's the author of this text, or as I'm going to show you now, I want to predict or estimate the position of a certain user in a building like this. So in this case, what I do is we take the output of the GNN for all of the nodes. So in this case, this is an example of the paper that I showed before. This is the graph. This is the GNN, and we take all of the outputs of all of the nodes, and we pass it through a certain function that takes into account all the embeddings, as in Marcelo's talk, the terminology, of the whole nodes. Now, it's important to note here that the ordering, in this case, that's a molecule, should not be important. And in that case, this function of the whole of all of the embeddings should be permutation invariant. I'm going to discuss that a little bit later. So I'm going somewhat behind. I'm going to talk about this very quickly. If are there any questions? No? So let's talk about permutation equivariance, and I think that with that the permutation invariant and equivariant will be clearer. So we've chosen graph convolutions to perform a prediction. Now, the first idea that comes to our mind is, for instance, in this case, we have signals or power measurements on each of these 16 APs, and we would like to predict at which position is my user. Probably the first idea you have is to make a 16-dimension vector and predict that output. Or in this here again, we may use the number of, I don't know, certain values that are in each of the drones to perform this prediction. So why not use a typical learning approach? For instance, we may use a fully connected network, which is simply a linear predictor. This is a linear predictor that we have our X, this is our signal, and this is the output. And the idea or the objective is to find my matrix that multiplies X to obtain the output. And if we combine this with a nonlinearity, we get a fully connected neural network. And if we stack all of this together, we get a deep neural network. So why not use this instead of our GNN? Naturally, and this is very easy to see, that here on the left, I'm showing this is the cost obtained during training for a fully connected network with several layers, and this is the one obtained by our graph neural network. And if you take a good look at this formula here, this H is actually a generalization of our S, of our graph shift operator, because well, it was the same, but we included a priori that we've defined before. So this should, the fully connected case should obtain a lower training cost. Now, and this should be clear in this example. Assume we have observed situations as the one on the left, where we want to predict, for instance, these are users, and these edges indicate that they have similar tastes. So we have observed this kind of cases here, and we want to predict the rating of 3. No? And both our GNN and the fully connected neural network will work when predicting this output. No, because they've observed it during training. Our GNN will probably simply average the ratings of users 9, 4, and 2 to predict the value of 3. Now assume we are given during test this other example. So in this case, the GNN will work too, because he will have learned that he has to average the ratings of 1, 5, and 12. In this case, because it's their neighbors, the neighbors of 6 are 1, 5, and 12. But the fully connected neural network will not know that, because this is for the neural network is a 12-dimensional vector, and he should have been exposed to ratings by 1, 7, 12, 5, and 11 to predict the rating in position 6. So now, was this clear or not? So again, because this is important, what I'm saying is the fully connected or any other learning method that consider my signal as a 12-dimensional vector will have to be exposed to this situation during training to see that actually he has for dimension number 6, take the inputs of dimension number 1, number 5, and number 12, and average them to predict the value for 6, whereas my GNN will have learned from observing this that he has to simply average the signals from neighbors, wherever they are. If they're here, okay, but if they're on the other side, okay too. So, to give like more formality to this, and again I'm going to go like a little bit fast here, but we may analyze this through permutation equivariance. And what's this? That's simply that the output of a graph neural network does not depend on the order we've given for our nodes. So that's what I was talking before. And that may be formalized by defining this permutation matrix that simply define as, I'm going to go quickly again on this, they simply define as a reordering of the nodes. And what we may see is that actually, and this is the theorem I want to show here, is that our graph operator is the filters are actually permutation equivariant. What does that mean? It means that if we take our matrix, our S matrix, we take our vector, we reorder the entries arbitrarily, but in a coherently. So for the same order for both the matrix and the vector, we obtain a certain vector x hat. If we do that the other way, we first operate and then we reorder, we obtain exactly the same. So that's what this theorem says. And here, well, GNNs, again, are the same as filter, but with a pointwise nonlinearity. So this applies too for our GNN. But what I wanted to highlight here is that the case on the left is actually a permutation of the one on the right. And that's why this works. So that's the message here. If the order, if the identity of each of the node doesn't matter, and the actual or the thing that matters here is only the relationship between neighbors, then a GNN is a good idea, and it will work, or should work. In a sense, it will multiply our data set, because here we're giving him or her, the GNN, this a priori structural information that will help him in also predicting the entry for node number 6. What happens when order does matter? It may matter, for instance, when we are going to predict the authorship of a certain document, each of the nodes is a word. So it's not the same, it's not like you permute the graph and it should be the same, we should obtain the same prediction. No. So in this case, we should be careful. We should not use vanilla GNN. We should, for instance, we may use feature augmentation. That's including a signal that also aggregates or includes some identity information for each of the nodes. Or we may use H-variant GNNs. There are the references here. You may ask, or you may have the following question. Well, that's all good, but this will only work if I have a perfect symmetry between these two. No, if I have, for instance, a graph as the one in here, and here I'm trying to show that these two parts are not exactly the same. They are somewhat different. There we may ask ourselves, what happens as everything falls apart? Well, no, there are papers, and that's the one I was talking about before, about stability of our GNN, that give conditions under which the graph output doesn't change much by changing a little bit the graph operator. So that was my presentation for GNNs. I have 1 minute and 20 seconds left. Are there any questions regarding this part? No? So then I'm going to just show you the application, and I'm going to use maybe 5 extra minutes. I don't know, Martin, if it's okay. So the problem was the following. This is at the Museo Nacional de Artes Visuales, down the street there, where there was like a big exposition that changed a lot on the museum. And the problem was that they had a system for visually impaired people, where they lend them a tablet and they could see some of the artworks at the museum, and they wanted a system that substitutes that. It was called Museo Amigo, the friend museum. So the problem was, well, is the user, in this case, this is a photo of the exposition at that time. The problem was is the user near Círculo y Cuadrado, and that's this part, this exposition, there by Cunha, a Uruguayan painter, or is he near Juan cree que el sol es una estrella, and that's these tables here. So that was the question. Naturally, a GPS won't work there. We're talking about a couple of meters or some meters apart. It's indoor, so GPS won't work there. No, so what are my alternatives? I may use another positioning system, such as a near field beacon, or we may use signals that are already available to infer our position. For instance, Wi-Fi, which is virtually everywhere nowadays. And in this case, the museum had only one Wi-Fi, but we had the generous contribution of Antel that provided us with 15 extra APs that we installed throughout the museum. And the idea is now that, given I have my phone, I measure the power of each of these APs, and I want to know if the user is either, for instance, outside, zone 16 is outside, or in zone, that was the piece of art I talked about before, is zone number 5, for instance. So, this is a classification problem that we've addressed in our original paper by using a fully connected network, and worked relatively nice. But we asked ourselves in one of our, in another work, if we could use GNNs. And I wanted to show this, to take these extra minutes just to show you an example. So, this is a graph classification problem. We have the power measurements on each of the APs. In this example, there are 5 APs, and we have 2 features per AP because they are double band APs. So we have a measurement for the 2.4 band and the 5 gigahertz band. So we have 2 numbers per AP, and we want to know if this signal to which of the, in this case, 4 areas belong. So we apply a GNN. This results in a certain vector, in this case, a 2-dimensional vector for each of the APs. Then, since in this case, the identity of each of the nodes is important, because it's not the same that the representation of this AP that is, for instance, in this room is a certain vector. It's not the same as if we rotate the whole graph. So we stack all of this representation and we pass it through a neural network, and that will give us what's the estimated position of our graph. Now note that in this case we lose permutation equivariance, and then we lose the advantages of that I mentioned before that permutation equivariance gave us. So how can we get it back? This I won't discuss in detail, but we may construct what's called an heterogeneous graph, where we have nodes and edges that represent different things. For instance, in this case, we have black nodes are APs and white nodes are zones. So we've transformed this problem into a graph signal interpolation problem, where we want to see what's the probability of the user being in these 4 possible zones. So, and that's all I had to say about that. The results are, well, it's a little bit better for the GNN, but that was not my objective here. And that's all I had to say today. Sorry for the delay. And if you have any questions, please go ahead.
Is there any question? I was wondering about this approach with the zones when you expand your problem. I have not worked with graph neural networks, so I was wondering if they are, if someone is using them to solve optimization problems over the graph neural network. For instance, you can use like that topology, maybe for try to find where to find another access point. No, where will be the optimal localization of a new access point? Is that possible with?
Yes, there are. And this is not only for graphs, but since it's like it has like many combinatorial problems that are NP hard, so there are many heuristics, and it's been approached by learning. And I think there are 2 typical methods for optimization, either in graphs or not. But it's, for instance, you have a set of instances and their solution, and you teach your system to learn new solutions for unseen problems. So in that case, you have to have like the instances and the solutions. And the other approach to learning to solve or learning to optimize, that's what that's called, is if you have an iterative method that, for instance, you run it until conversions, for instance, and it can be seen as iterative, and you may think of it as several stack layers. So in that case, what the system learns is, for instance, you give them 10 iterations, and you may see this as 10 layers, and the system learns to solve it as fast as possible in those 10 steps you are giving to it. And that's called algorithm unrolling. So that's the 2 approaches. So if you want to look for the keywords are algorithm unrolling, or the other is learning to optimize, or learning to optimize. And there are several papers, there are several surveys by I think it's Joshua Bench, but those are the two keywords. Any other questions?
Yes, I was wondering on what type of format your graph normally have in your learning problems. It's not an image per se.
No.
It's a graph structure.
Yes.
So which format, just out of curiosity, is the data?
Well, that's a good question. Because there are no there are no formats that everybody uses. So there are 2 or 3. For instance, Gephi has one that's called GXMF, I think. That's an XML, I think. There are 2 or 3, but no. Typically, like they give you the raw data and you have to construct your graph. And for instance, you pass it through 5G or whatever. But that's a problem. For the file specification for saving in your hard drive the graph, I think that's not like there's one standard file that everybody uses to share their graphs.
And is it easy to find data? Because if you want to
yes. We have in the course we give with Marcelo and other colleagues, we have like a section of the data set. There's the snap from Shureleskovich. There is there's Karel, obviously, and there is a benchmark for graphs specifically. That's called Marcelo, OBS, no, OBG. Yeah, something like, there's a open benchmark for graphs. I think it's OBG, open benchmark for graphs, and that has like this kind of problem. For instance, the citation graph, and it has the data ready to be loaded by PyG, and it has like a scoreboard for what's the method that obtains the best results or the fastest result or whatever. So there's like there are several efforts in standardizing how results and how to save them, but I don't think there is like this is the standard or this is the file format that you should use. Any other question?
Okay, and we'll see you tomorrow with the opening ceremony of the conference.